Hello and welcome to today's lesson, which we're going to look at terminal velocity in a practical context, and we're going to see how we can look at terminal velocity from experimental observations. So this particular lesson falls in the combined science topic of forces for physics. So what we're going to look at in today's lesson is we're going to try and describe what terminal velocity is, accurately understand how an experiment can determine terminal velocity, and understand how surface area affects terminal velocity, which links into the following part of the AQA Combined Science specification. In particular, looking at this idea that an object falling through a fluid initially accelerates due to the force of gravity, then eventually the resultant force will be zero and the object will move at a terminal velocity. So, when an object falls through a fluid, either a liquid or a gas, there are two forces on the object. Weight, which always acts towards the center of the object causing the gravitational field, which in our example is the Earth, and air resistance, which acts against motion. Now, air resistance is caused by the object pushing air particles out of the way every second as it falls. So the larger the surface area of the object, the more air pushed out of the way every second, so the larger the air resistance produced. Now, objects which have a small surface area produce a small air resistance, okay, and we call them aerodynamic objects because they don't push out many air particles when they fall because of their surface area and their shape. Now, weight always acts towards the center of the Earth and is calculated with the equation weight equals mass times by gravitational field strength, which is an equation you're going to have to memorize for your examination. Now, when the object first falls, the weight is larger than the air resistance, which gives us a resultant force downwards because there's a larger downward force compared to the upwards force. So this will give an acceleration downwards because Newton's first law of motion states that there will always be an acceleration in the direction of the resultant force. So if we've got a resultant force acting downwards, we have an acceleration acting downwards. Now we can plot this out on a velocity time graph because the gradient of a velocity time graph is the acceleration. So if we've got constant acceleration downwards, we're going to get a nice constant straight line going upwards. Now, as the object falls through the fluid or the gas, because it's moving faster, more air particles are pushed out of the way every second, so that will increase the air resistance. So now this will lower the resultant force, which is the difference between the air resistance and the weight. This will lower the resultant force and therefore lower the acceleration. Because from Newton's second law, we know that the resultant force and the acceleration are directly proportional to each other. So if the resultant force decreases, the acceleration decreases, and as a result, okay, the object will still be increasing in velocity, okay, however, it will not be as increasing at a great rate, which we can observe with a curved line going downwards, or slightly downwards, on this particular graph, on this velocity time graph. Now the object is still increasing in velocity because the line is still going upwards, but it's not increasing at the same rate it was before because it's curved slightly. Now, eventually, after the object has fallen for a prolonged period of time, the air resistance and weight are the same size, so therefore there's no resultant force, so there's no acceleration, so the object moves at a steady speed. Now, the object has hit terminal velocity. It is the speed that it can go when it is falling its maximum speed. Now we can plot this out on a velocity time graph with the flat line that indicates to us the object has achieved terminal velocity because there's no more acceleration, so the gradient of the line will be zero because the acceleration will be zero. And remember, it's a flat line, but it's not on the x-axis because there still is a velocity because we're still traveling at a particular velocity, so it just won't change from that speed. Now, you've got to remember this pattern will be followed for any object falling in a fluid. Now, we can consider many applications of terminal velocity in the real world. So an example of this will be a ball being dropped in cooking oil. Now, the ball will fall through the oil to the bottom of the tube. Now, we can predict the motion of the ball with Newton's laws of motion. So, because cooking oil is a liquid, so it's a fluid. Okay, so as a result, we can just follow the same steps that we had before. So when the object falls in the fluid, there are two forces on the object, air resistance acting against motion, and weight acting downwards towards the Earth. Now, at the start of the journey, the air resistance is smaller than the weight, well, the fluid resistance in this case, because it's a liquid, so there's a resultant force downwards, so the object accelerates downwards. Now, as the object accelerates, the speed increases, so more fluid particles are pushed out of the way every second, so the fluid resistance increases, whilst the weight stays constant. So the resultant force downwards is smaller, so the acceleration downwards is smaller, so this causes the speed and the air resistance to continue to increase. Now, over time, eventually, the air resistance equals the weight. There's no resultant force on the object. There's no acceleration on the object stays at a steady speed, and this is called the terminal velocity. So the object will have inertia because it's maintaining the same speed in the same direction when there's no resultant force acting upon it. So that particular effect we call inertia, and it comes from Newton's first law of motion. Now, the object will maintain this terminal velocity until it hits the bottom of the cylinder. Now, throughout the journey, the weight acting on the object stays constant. It's the air resistance which changes throughout the journey. Now, if there was no fluid, say the object fell in a vacuum, there will be no air resistance, so the object will constantly accelerate down due to weight, because the only force acting on this fallen object would be the weight. So all objects would fall to the ground at the same rate because they've only got this force of weight acting on them. Now, this was actually demonstrated on the moon, where there's very, very little air resistance. There is some, but it's a very, very small effect, where the objects of a hammer and a feather were dropped and fell at the same rate because there was very little air resistance acting on either object. There was only weight acting downwards, so they both accelerated to the ground at the same rate. Now, when doing an experiment with terminal velocity, it will be very difficult to measure the terminal velocity of an object. You will get inaccurate results. It will be difficult to measure when the object would have obtained terminal velocity, because if you just let an object go and let it drop, it undergoes the acceleration at the start, then the rate of acceleration decreases, and then it hits terminal velocity. So as an experimenter, it will be very, very difficult for you to actually understand when it obtained terminal velocity. Now, it also will be difficult to measure the timings of an object, as the object fallen occurs very, very quickly, so it would drop really quickly. So as a human being trying to measure the motion of an object, it will be very, very difficult because it's moving so fast. So, to solve this particular issue, you would use computer sensors and light gates, as this would reduce the uncertainty in your timing measurements, as there would be a smaller random error due to using a computer sensor and light gate. Don't say that there will be no random error or no human error in this particular process, because there still would be, because you've still got a human setting up the computer sensors and the light gates, and a human still interpreting this computer sensors and the light gates. Now, as well as that, it's very, very unlikely in any class experiment you would do that the object would have achieved terminal velocity, as it takes a relatively long time of falling to achieve terminal velocity. For example, in air, it would take approximately 30 to 40 seconds of falling to achieve terminal velocity. Now, in most class experiments, objects tend to be fallen for a maximum of 5 to 6 seconds. So, unfortunately, we can't really achieve terminal velocity because it's that final step in the actual process of the journey, not at the initial step, so it actually takes some time to achieve terminal velocity, and in most situations in a classroom, you won't have an object falling enough for a prolonged period of time to obtain this. Now, to solve this, you would have to increase the height in which the object falls in the fluid. So you would have to drop it from a very, very high distance normally for it to achieve a terminal velocity in the fluid. So in most classroom settings, you would never actually achieve terminal velocity. You will probably start to achieve that slowing down of acceleration in the classroom, but you're very unlikely to achieve terminal velocity. Now, just to clarify, it doesn't matter what fluid the object is in, if it falls for long enough, it will achieve terminal velocity. So this fluid could be oil, this fluid could be water, this fluid could be air, any liquid or a gas. If an object is in motion in that particular fluid, it can achieve terminal velocity. So look out for examination questions where they look at an object moving in a fluid like water, like oil, like the air. All situations when an object falls in the fluid, it will eventually achieve terminal velocity. It will eventually achieve this maximum speed. It can go no faster than. Now, let's see if we've understood what we're covered in today's lesson. We know that velocity is a speed in a given direction. Acceleration is the change of velocity per second, calculated by change of velocity over time taken. Now you can work out the acceleration of an object from the velocity time graph, and you can work out the distance travelled by an object from the area under the line of a velocity time graph. Now an object falling through a fluid initially accelerates due to the force of gravity, but eventually the resultant force will be zero and the object will move at its terminal velocity, and that is the constant speed of a fallen object when it's been fallen for a prolonged period of time. And it will occur when the air resistance and weight are equal in size, and it's the air resistance that's varying throughout the journey, not the weight. So in today's lesson, if we have learned, we can describe what terminal velocity is, we understand how experimentally can carry out an investigation, look at terminal velocity and the issues with those particular investigations, and then finally we can understand how surface area affects the terminal velocity. Now, hopefully you've enjoyed today's lesson, looking at the practical application to terminal velocity, and have a lovely day.